I see some people are still in waiting room, so I guess you will handle that, right?
Yep.
Okay.
Yep. I got the waiting room.
Okay. Okay. Thank you. Yeah, I will start to present. Hello everyone. My name is Menjun Xie. I'm from University of Tennessee at Chattanooga. I'm an associate professor here in the Department of Computer Science and Engineering. And I'm also the acting director of the UTC InfoSec Center, which is CAE CD. And today, it's my great pleasure to present this joint work titled ReLF, Scalable Remote Live Forensics for Android. This is a joint work with my PhD student Ruipeng Zhang, as well as my collaborator, Dr. Jiang Bian from University of Florida. And this work actually has been published in 2021 IEEE International Conference on Trust, Security, and Privacy in Computing and Communications. Here is the outline of this talk. First of all, we will give a brief introduction about the problem, the motivation, and background for scalable remote live forensics for Android. And then we present our approach, followed by evaluation and the evaluation results. And then after that, I will make a demo. Actually, this is not a live demo because of the unexpected situations that could occur in the live demo. So we record a demo and we'll play it. But through this demo, you should be able to see get an idea about how their tool is supposed to use and its capability. And at last, I will conclude this talk. So here, first is about the motivation. So nowadays, workspace has been extended to mobile devices, given their wide usage in daily work and businesses. And at the same time, the cybercrimes involving mobile devices are also quickly growing. However, it's not easy to collect artifacts for cybercrime investigation from those mobile devices in a responsive, scalable, and efficient manner, especially when the suspected devices are not seized and the cybercrime activities are still ongoing. Let's look at two scenarios. Here, imagine you are CISO, Chief Information Security Officer of a company, and you are supposed to oversee the security of their intellectual properties or IP of your company. And recently, you noticed, or maybe you were notified that certain IP information had been leaked from the company to one of the company's competitors, and most likely through an Android mobile device. And now you want to find out who did that or who is still doing that, and how their IP theft has been done through mobile devices. So these questions are very important, but the more important question is how you can achieve your goal, essentially conducted the investigation. Suppose we are able to conduct a remote live forensics for Android devices. Then with that capability, the first thing you can do is to triage, essentially during which you can narrow down, just like the triage in an emergency room, you can narrow down a list of suspects by extracting and inspecting the log files, the browser histories, and other similar related data files from those suspicious devices. So here on the right side of the slide, we show two screenshots. The top one shows the collected browsing histories from a Chrome browser. And the bottom one shows acquired database file of Facebook Orca application, which contain the Facebook application information. Then with those data files and other related information, you can do much in-depth investigation, and you can narrow down to a few or even one suspect. So that will help you a lot to get more understanding of the suspects, as well as how their IP theft could possibly be done. In addition, because of the mobile device has many powerful sensors, so for example, GPS sensors, so you may, if you find that the GPS recordings is also available, you can actually retrieve that information and locate the device in question. And all these can be done when the device is still being used by a person. So for this second case, suppose Android malware spread has been detected and reported by IT network monitoring facility. As a CISO or a related admin, you want to use the Android forensics tools to investigate the malware infection in your organization. For example, you want to understand how many devices have been affected, and what are the files or information being, for example, being compromised. With the help of this forensics tool, you can scan or enroll mobile devices to search for their malware application. And you can also access the impact of the malware infection. For example, you can retrieve live malware samples as well as trace data, such as the chat and call histories from the infected devices. And finally, you can notify the affected employees and stakeholders to prevent further damage. So you can see that the Android forensics can be very crucial to information security in an enterprise environment, and where Android devices are widely used and managed as for the business. However, traditional data extraction approaches to Android forensics are not able to deal with incidents responsibly and at scale. And here we list some traditional ways of extracting data from Android devices. The first category is physical data extraction, which is usually done by directly reading data from the flash storage of the device. And for example, like through JTAG or chip-off methods. Those methods can bypass certain system restrictions and extract data from damaged or locked devices. However, it requires physical access to the device and risks altering the hardware and make the hardware totally unusable or inaccessible. Finally, it cannot retrieve volatile data from the device because the device is turned off before data acquisition. The second category shown in the middle is the offline logical data extraction, which usually uses the Android recovery system to image the whole disk. However, it has similar restrictions as the physical data extraction. For example, require physical access and cannot retrieve volatile data. And on the right side is the last category, online or live logical data extraction. In this category, it certainly can retrieve both volatile and non-volatile data. That's an advantage. However, existing methods essentially are limited by the operating system restrictions, and it still requires physical access. Okay, so we certainly need a more advanced mechanism to help us to overcome those restrictions or shortcomings. So here we show our approach. So we proposed the approach to perform digital forensic operations such as evidence collection, examination, and reporting remotely from an operating computing device. Here specifically referred to Android devices. And this remote live forensics is not meant to replace existing Android forensics methods. It's really to complement existing methods. We do not believe one method can cover all scenarios. Okay. However, we do believe this remote live forensics can bring many more benefits that are not available from existing methods. For example, it can extract data in real time. It can extract data without need to seize the hardware. It also offers much better flexibility and mobility. The last, it's easy to scale, which is not really not available in any of the existing open source tool or their system in academia. So we think that is also very important for doing the forensics in an enterprise environment, because usually they are many. For a large enterprise, they may like hundreds of devices at the same time being used, and this kind of scale require a specific tool to address the challenge. So here shows an overview of the ReLF system. You can see it's based on a typical client-server architecture. The ReLF server has a web UI, a user interface, for administrators to access all enrolled devices and collected artifacts. It's also the place for administrator to start data collection tasks. And the server front ends communicates with the ReLF clients, while the server workers process the collected artifacts. So you may have multiple workers and multiple front end. And if you have a really big enterprise system to monitor, I mean, many more devices to monitor, you may consider to deploy an additional load balancer and to proxy front end for better performance. And all extracted artifacts will be stored in the data store at the server side. The ReLF client is installed on an Android device and communicates with the ReLF server through a communication module. And it processes data collection tasks issued by the server and will extract artifacts from the device via client workers. So there may be multiple client workers on a device. And those workers in turn will call the Android API or the ReLF native service. So the ReLF native service is a customized service we developed to provide access to the underlying Linux file system. The idea is to help the client retrieve sensitive system information, which is inaccessible from the Android world. So it's essentially not available through the regular Android API. So before the artifacts can be collected from the Android devices, we need to deploy the ReLF client on those devices and complete the client enrollment process. It's not like any type of traditional capturing method that you can just seize the device and then you can conduct their acquisition and then analysis. For our approach, actually, it's a more kind of managed manner. For Android devices managed by enterprise IT, an administrator can install this ReLF client as either a user app or as a system app. The user app is just like any other regular Android app, and it can be installed from an app store managed by their enterprise or through other means. But essentially, it introduces list changes to their existing operating system or the firmware. But it does not provide the full capability of their of the acquisition, because certain the user application there is a limitation or there a restriction on the information that can be retrieved. So if you want to get full scale of the capability, you need to install the ReLF client as a system service or system app. This installation does require customization to the Android OS. However, it provides much richer data collection functionality compared to the user app mode. After the app is installed on the client side or on device, then the ReLF client will generate a client certificate and enroll itself with a ReLF server. And during the enrollment, both the client and server will exchange their digital certificate for mutual authentication. And finally, the server will automatically initiate an interrogation query to the ReLF client to retrieve the device information and set up the client profile. So this profile will help investigators quickly identify enrolled devices and run data collection tasks. And here shows the data extraction process. So once a client is enrolled, an investigator can launch data acquisition tasks on the ReLF server through their web UI. The server enqueues those tasks in the front end, and the ReLF clients periodically pull their server to check for new tasks and process them. So the communication between client and server actually is not synchronous, especially when the client retrieve a task. It will actually do their job in an asynchronous way. So after getting the task, a ReLF client will extract the requested artifacts from the device by calling either Android API or the ReLF native service. And at the end, the ReLF client will encode those artifacts into a binary format and send them back to the server through a secure channel. In our implementation, this secure channel is HTTPS. And here lists the artifacts ReLF can acquire. All the artifacts are defined in the digital forensics artifact repository format, which allows users to create their own artifact definitions using the format. As you can see, ReLF introduces a variety of Android-specific artifacts, including system information and sensor data, which are shown in the table on the left side. Some of those artifacts are fully supported, as shown with green checkmark, which means they can be collected no matter which client is deployed. In other words, some others can only collect it when they're, in other words, they can be acquired by a ReLF user app, because their user app has limit compared to the system app. The capability is basically smaller. And you can see that some artifacts are marked with star. That means they can only be collected through the system app. And some capabilities are not supported yet. Okay. So next I will present the evaluation. and the experimental results from the evaluation. And before that, I want to briefly talk about the implementation of the ReLF. So we have a client and server. The ReLF client is essentially the app and system service developed from the scratch. But for the server, we actually leverage an existing live forensics platform named Jiang Rapid Response. That was developed by Google and was used quite widely for laptop computer, desktop computer, those servers, live forensics. So we consider to believe because those GRR rapid response has developed much very great functionality. So we decided to leverage its existing modules. However, still significant changes have been made to make it work with the ReLF client. So to evaluate the ReLF client's energy efficiency, as well as the ReLF server's scalability, we set up the following test bed. Essentially, we first used the physical devices to test the ReLF client's energy efficiency, and we developed the different workloads to test it. The physical devices include Nexus 9, Nexus 5X, and Moto G5 Plus, and each of them runs a different version of Android OS, as you can see from the slide. And we also have evaluated the scalability of the server using 128 virtual Android devices that run a variety of Android OS versions. In addition, we set up a ReLF server in a virtual machine with 4 CPU cores and 8 GB memory in a remote cloud. It's the commuting cloud. And both the virtual Android devices and the ReLF server are running in that cloud environment. So first, let's look at the ReLF client's energy consumption. We have 3 different settings. So in the baseline tests, we measure the baseline energy consumption when there is no data collection. And so it's marked or it's illustrated with dotted line. And we have type 1 test and type 2 test. And for type 1 test, we measure the client's energy consumption when collecting persistent data. And in type 2 tests, we basically measure the client's energy consumption when collecting connecting volatile data. So you can see that on the essentially on the this left-hand side, we have the on the top, essentially the workloads, different workloads when the device is being charged, okay, and the bottom 3 subfigures showing their energy consumption when it's not charged or it's on the battery. That's why you can see the battery level decrease from 100% to lower than 80%. But here it's basically just we use a device to measure the power consumption. Okay, and essentially what you can see here is no matter it's type 1 or type 2, the difference between these type 1, type 2 tests and the baseline is very minimal, is very small. So that suggests the ReLF client introduced almost negligible overhead when being operated, okay, from either a charged mode or battery mode. And we also look at the energy consumption of ReLF client with type 1 test, which is essentially for persistent data acquisition on Moto G5 Plus with different polling intervals. So you can see that we tested with 5-minute interval, 10-minute interval, 15-minute interval, and 20. And we find that essentially, in general, the larger the interval is, the power consumption, the less power consumption will be. So that's about the energy consumption. Overall, we found the ReLF adds a little energy consumption overhead compared to normal operations. And regarding the scalability, we have essentially tested this scalability under fast client polling and slow client polling. So here we set two intervals for polling. The T1 is 600 seconds, means 10 minutes, and that's for the left. Sorry, for this one, for these two figures, and as well as this one. So the left figures essentially with T1 interval, polling interval, and the figures on the right are with T2, which essentially is a random number less than 10 seconds. So this is the fast polling, this is the slow polling, right? And these are kind of the data collected from 128 clients, virtual clients. And we can see that the top figures on the left, on the top left, show that all the 128 clients can complete that acquisition in roughly 2 times the polling interval. So here, this is the 600. This is 600 seconds, basically the polling interval, and then we can see all of their data acquisitions tasks finished around essentially at the 1,200 seconds, so 2 times. And the top right figure basically showing the server has consistent memory utilization. So this is a memory utilization, and the bottom one shows the CPU utilizations. And it's pretty stable for slow polling tests. For the fast polling tests, we can see that we have some spikes for their CPU utilizations. Essentially, during this time, it's if you map this figure with this figure, essentially at the beginning, the data acquisitions. So it may cost, the CPU spikes may caused by the data acquisitions. And these two figures basically showing the network bandwidth usage when we conducted 2 tests. So in general, it shows that the network utilization is pretty low. There are several spikes here. We suspect those spikes are caused by the user interaction with the server, because during those times we have essentially admin have some interactions through the web UI. But in general, we can see that most of the time, no matter the CPU, memory, or the network, the utilization is pretty flat and low. And remember, this test is, the server is only with 4 virtual CPUs and 8 gigabytes of memory. So it's a small server, but it still can handle a quite large number of clients. So on this slide, we show the comparisons between ReLF and other Android forensics tools that are available through the literature review. So we can see that ReLF has better support in terms of the Android system compatibility. So during the submission of our paper, we found that our system can support the Android OS from 5.0 to 11.0, while others support older versions. So yeah, we understand that those open source projects may not be supported anymore. But still, we believe that those systems, not just considering compatibility, but looking at the artifacts supported, our system support many more artifacts types than others. And in addition, ReLF also support multiple devices. So not like the other open source free applications or systems, the ReLF is able to support multiple devices. And it allows the administrator to triage before the actual data collection and organize those artifacts device by device. And last but not least, it's free and it's open source. So the link to the source repository is shown in the last slide. Okay, we acknowledge that the ReLF as a forensic tool may raise security and privacy concerns among its users. So first of all, the integrity and the confidentiality of the collected artifacts are preserved during data extraction and transfer, assuming the device Android operating system is not compromised. And ReLF leverages HTTPS and mutual authentication to prevent server or client spoofing as well as data leaking during the data transfer. In addition, the collected artifacts are only stored in memory on client side, not on a local file system at client, to prevent them from leaks and unauthorized tampering. And we expect the organizations that deploy ReLF to obtain the consent from their users in the first place. And we also want to make sure users are fully aware of the ReLF activities. So in our implementation, when the client is running, it will create a sticky notification on the screen to make user aware. So next, I will show a demo. So as I mentioned, this is a recorded demo. So let me switch. Sorry about that.
All right. Do we got any questions?
Hello, everyone. I'm Ruipeng Zhang.
Sorry.
Sorry.
Is that okay to make a demo? Or?
Yeah, go ahead. Play it.
From the University of Tennessee at Chattanooga. Dr. Xie and I started the ReLF project a few years ago in order to bring remote live forensics to Android devices. With ReLF, forensic investigators can easily triage a large fleet of Android devices and extract digital artifacts from these devices. The forensic operations are done on the fly while the device is turned on, and data extractions are carried out without requiring physical access to the device. To give you a closer look at the capabilities of ReLF and how it can help people respond to cybersecurity incidents quickly, let's begin with some demonstrations. Here in front of you is a ReLF dashboard. The dashboard is adapted from Google's GRR Rapid Response platform, with a lot of changes made to enable remote live forensics on Android. On the left-hand side, we have several menus lead to platform management pages. The cron job viewer page presents a list of scheduled jobs on the platform and allows you to create, start, pause, and destroy jobs. This function is very useful for periodic triage and large-scale data extractions. If you just want to start a one-time data extraction task on multiple Android devices, you can go to the Hunt Manager and create a new hunt. The new hunt wizard will guide you through the configurations of a hunt, such as choosing a data extraction workflow to perform on each Android device. The scale and time span of the hunt, the report output format, rules that filter out specific devices from which we want to extract data, and the final summary of the hunt. Then you can start, stop, or reconfigure the hunt on the Hunt Manager page. The platform also provides statistics about the ReLF clients. And server settings on the platform. To see all the Android devices that are enrolled on the ReLF platform, you can press the magnifier button on the top right. Here we have 2 enrolled Android devices. One is online with a green circle at the beginning of the list, and the other is offline as indicated by a red circle. The subject column displays the unique IDs of the ReLF clients, which can identify Android devices on the platform. The rest columns offer an overview of the Android devices and ReLF clients. When clicking on a list item, we'll be taken to the details page of the device. This page provides brief information about the device, such as versions of the operating system, Linux kernel, and the ReLF client. It shows several important timestamps of the device and lists all network interfaces. You may also view the complete details about the device by clicking the Full Details button, or see past device information by selecting a version from the version drop-down list. Meanwhile, there are several more menus showing up on the left side of the page. First, the Start New Flows page lets us start a new data extraction workflow on the current device. It is just like what we have seen in the new Hunt wizard on the Hunt Manager page, but the workflow we choose here starts immediately on the selected device only. Once the workflow is created, it will show on the Manage Launched Flows page. From this page, you can see a list of ongoing, completed, and failed workflows for the selected device. You may also destroy, duplicate, or create new hunts from these workflows. The results of a workflow is displayed on the bottom panel in the Results tab. The Browse Virtual File System page lets an investigator to search for arbitrary files on the device file system. First, select a directory you want to inspect. Then click on the Refresh Directory button to sync the file list with the device. You may also choose to recursively sync the directory until a maximum depth by clicking on the second button. If you click on a directory or file, its statistics will be displayed in the bottom panel. You can also collect or recollect the file content or directory by clicking on Collect from the Client or Recollect from the Client button. The content of a file can be viewed in the Text View tab or the Hex View tab. You can also download the file to your PC by clicking the Download button. Additionally, we can view ReLF client's load statistics on the Client Load Stats page. This page shows the recent CPU, input-output, memory, and network usage of the client. Next, let's see how ReLF helps forensic investigators deal with a cybersecurity incident. Let's assume you are told by one of your colleagues that a strange app named Rat appeared on his work phone not long ago, and he is asking you, the company's cybersecurity specialist, to investigate the app. You know that his work phone is enrolled on the ReLF platform and the ReLF client is running on the device. So you first start an artifact collector flow to pull a list of installed apps from your colleague's phone. To do this, you go to the Start New Flows page and select Collectors, Artifact Collector Flow from the tree list, and then select the Android platform from the platform menu. Double-click on Android packages, and finally, launch the flow. After a minute or two, you will get a list of installed apps and their detailed information on the Manage Launched Flow page. Since the list is very long, you download the result as a CS file using the download button. This allows you to use other tools such as Excel or text editor to quickly identify the app in question. Let's try to search for the app's name. Here you can see the app's name and its package name, as well as its source directory. Here you find the app is in this directory. It's time to pull the app from the phone using the virtual file system. You simply navigate to the app installers directory from the Browse Virtual File System page. And collect the APK file from the device. Now you have a live sample of the suspicious app, and you can match it to a malware in the malware database. This app is identified as a spyware that scans and uploads user data, such as contacts, messages, call logs, and photos from the victim's device to a remote server. To see if the malware is still running, you can initiate the list process workflow. When completed, this workflow will give you a list of processes on the device. Their process IDs, user IDs, open files, etc. Using the filter, you can find out the malware is still running on the device. And it connects to some local databases. To collect the traces of this malware from the infected device, you use the virtual file system function to browse the app's data directory. You find out its databases, and then you can pull those database files to your workstation and investigate it using SQLite browser. The malware stores a copy of stolen data in its database. And it keeps its inserted flag to indicate whether the record is uploaded to the remote server or not. To quickly locate the infected device, you launch another artifact collector workflow called Android location. This workflow returns an accurate GPS coordinate of the infected device. Now you have the device location. You can inform your colleague to turn in his work phone to you for a more thorough examination. That's all for our short demonstration.
Okay, so go back to my presentation. So next part is conclusion. Yeah, so in this talk, we have introduced ReLF, a large-scale remote Android forensic triage and live logical data acquisition system. The ReLF's design enable scalable and feature-rich remote live forensics for Android devices. And we have evaluated ReLF's features, energy consumption, and scalability, discussed its security and privacy mechanisms, and demonstrated its usage. And we want to thank National Security Agency for the support for this project, as well as University of Tennessee at Chattanooga for its support for the study. And at last, we also want to thank Communion Cloud for providing experiment resources for conducting the study and evaluation. And as I promised, we have open sourced the project. You can find it on the GitHub with this link. And if you have any questions, you are welcome to contact me. And thank you.
All right, all right. Do we have any questions for Menjun? If you do, you can just drop them in the chat.
I just have a quick question. I wonder how this app is kind of different from those mobile device management.
The mobile device. Okay.
Yeah.
Can you give an example about the mobile device management tool? Or?
I mean, I'm not sure any maybe open source tool yet, but I think I feel like because this requires you initially enroll the user into the system, right? So it's more kind of suitable for the company that will install on their work phone, right? So
yes.
that mostly company, that have this I think most now IT will install some kind of mobile device management tool. I think there are many of tools. So they will kind of manage the installation, collect information of the employee device. So just kind of see, I think some like maybe similar functionality here. I guess maybe, yeah. I see a chat that they're talking about, yeah.
Oh, okay. Yeah, I think so. Yes, the mobile device management tool definitely they are commercial platforms. I mean, can do all these different tasks. However, it's really started from our initial kind of the idea for developing this is to better understand the Android forensics for essentially for cybersecurity study, research, and education. And there is no really readily used available tool for us to conduct our research. We listed a bunch of open source and academic work conducted before, but all of them are really for individual investigation. And we feel there's a need for us to investigate and develop such a tool to fill in the gap for the large scale, because individually it's already, I mean, many tools that can help us to understand the individual behavior of the Android malware, but and also the how to say the behavior of, I mean, on a single device. But if we want to have a big picture and understand their infection in a larger kind of scope enterprise environment, we feel there's a need, and also at the same time there's a gap here for this live forensics. So that's we agree that definitely there are many tools that can be done. I mean, may have the similar functionality, and for commercial like mobile forensics, they may have those functions, but certainly that's not very easy to access.
We had one comment in the chat. Dr. Jonathan Jenkins said MDM allows downstream policy enforcement on the mobile.
Yeah, I'm not quite familiar with those MDM, but I understand certainly that's it's it basically with this policy enforcement that many things can be implemented through the MDM, I guess.
Yeah, I think it's just I really like your work. You know, it's open source. I definitely take a look because I'm very interested. I think that can be add some kind of functionality to implement some MDM, like the example that you have. You know, you try to check whether this is a malware, and you know, for company wise, you might want to immediately uninstall it. Right? You might want to immediately, like, you know, stop the process, you know, to prevent any further, you know, data leakage of your company phone, right? So that's, I think, you know, they can also be implemented on the platform. That's, you know, MDM usually will do is that downstream. So they will try to, based on the policies, and they will, let's say, you know, find the malware and uninstall the malware, you know, limit your capability to doing different things. Yeah.
Yeah, I certainly, but I would like to point out there are still a pretty big difference between this MDM and our system. Essentially, I think the major difference lie in the perspective of looking at its objectives. So our tool, as well as I think the GR, we mentioned that they built this tool really for from the perspective of forensics. So some of the operations are pretty, I would say, pretty strange to normal MDM, especially, for example, you can retrieve the system state, those volatile information on volatile state. And actually, one area to expand is to, for example, you may be able to really enable some kind of memory forensics, as long as, I mean, we didn't include that, but it's possible. So which certainly will be not be very normal for MDM, in my opinion. So because I guess that in general, MDM as a comprehensive management tool should also consider like the security management, but their primary purpose probably still under application management, under regulate how those applications should be used, but may not be that comprehensive to investigate when something bad happens, you know. So I guess that's a kind of, they overlap a lot, but there's still a big differences there, and that's my thoughts. Yeah.
Yeah, thank you very much.
Mm-hmm.
Are there any other questions? All right, if there are no other questions, Menjun, I just want to thank you for your time.
Thank you.
Giving this presentation. You know, we don't get a demo every time somebody gives one of these talks, so I think that was very interesting. So thank you for that.
Thank you. Yeah. If you have any further question, yeah, feel free to contact me. Thank you very much.
Do you want to drop your email address in the chat box?
Oh, yes, that's my first name dash last name at utc.edu. So Josh, I guess this is the end.
Yep. Yeah, we're gonna go ahead and wrap up. So just thank you again, and thanks everybody for joining us for our November Tech Talks.
Thank you.